Imagine harnessing the power of the sun, not with solar panels, but by recreating the very process that makes the sun shine. This is not just a dream, it's a scientific endeavor that has captivated minds for decades. This is the ambitious goal of McGinty AI's groundbreaking invention, the Sun in a Jar Reactor, a project that aims to bring the power of the stars down to Earth. This revolutionary device promises to unlock a new era of clean, limitless energy by replicating nuclear fusion, the same reaction that powers our very own star. Imagine a world where energy is abundant and clean. For centuries, the dream of controlled fusion has seemed like something out of science fiction. Stories and visions of a future powered by fusion have inspired generations. Now, thanks to advances in materials, science, artificial intelligence, and a deep understanding of plasma physics, that dream is finally within reach. The barriers that once seemed insurmountable are being overcome. The Sun in a Jar Reactor is more than just a technological marvel. It represents hope for a future free from fossil fuels and their devastating effects on our planet. It symbolizes a shift towards sustainability. In this journey of discovery, we will delve into the heart of this revolutionary technology. We will meet the brilliant minds behind this innovation. We will explore its intricate workings and unravel the science behind its elegant design. From the smallest components to the grand vision, every detail matters. Join me as we embark on an exciting exploration of the Sun in a Jar, a beacon of hope for a brighter and more sustainable future. Together, we will witness the dawn of a new energy era. At the heart of the Sun in a Jar Reactor lies a torus, a donut-shaped structure that forms the reactor's core. Imagine a giant metal donut, meticulously crafted with precision engineering. This shape is not arbitrary. It's crucial to containing and controlling the incredibly powerful forces at play within the reactor. The torus acts as a container for the plasma, the superheated state of matter where fusion takes place. The smooth, continuous curve of the torus ensures that the plasma can flow freely without encountering any sharp corners that could disrupt its delicate balance. This uninterrupted flow is essential for achieving and maintaining the extreme temperatures and pressures needed for fusion to occur. Confining the fiery plasma within the torus is no easy feat. This is where the MWave harmonic field comes into play. Picture an invisible cage woven from precisely tuned electromagnetic waves holding the superheated plasma in its grasp. This innovative technology, developed by McGinty AI, is key to the Sun in a Jar Reactor's success. The MWave system generates a complex three-dimensional electromagnetic field that interacts with the charged particles of the plasma, effectively trapping it within the torus. Think of it as a magnetic bottle where the plasma is constantly pushed inwards, preventing it from touching the reactor walls. This contactless confinement is crucial because the plasma's extreme temperature would instantly vaporize any material it comes into contact with. While the MWave field provides the initial confinement, a system of powerful superconducting magnets further tames the energetic plasma. These magnets, strategically placed around the torus, generate a magnetic field that interacts with the plasma's own magnetic field. This interaction creates a delicate dance of forces, guiding and controlling the plasma's movement within the torus. Imagine a ballet of charged particles swirling and spiraling within the reactor's core. The magnets act as invisible hands, subtly influencing the plasma's choreography, ensuring it remains stable and doesn't come into contact with the reactor walls. This intricate interplay of magnetic fields is a testament to the ingenuity of the Sun in a Jar Reactor's design. To achieve fusion, the plasma inside the reactor needs to reach temperatures hotter than the core of the Sun. This is an incredibly challenging task, requiring advanced technology and precise control. This is achieved through a combination of methods, each playing a crucial role in igniting the fusion reaction. These methods work in tandem to ensure the plasma reaches the necessary conditions for fusion. First, a small amount of hydrogen fuel in the form of deuterium and tritium isotopes is injected into the torus. These isotopes are chosen for their favorable fusion properties. Then powerful microwaves, similar to those in a microwave oven, but on a much larger scale, bombard the fuel. These microwaves are specifically tuned to maximize energy transfer to the fuel. These microwaves energize the fuel atoms, stripping them of their electrons and creating a swirling cloud of plasma. This plasma is a hot, ionized gas that is essential for the fusion process. Heating the plasma to the required temperatures for fusion requires even more energy. This is a critical step, as the plasma must be extremely hot to sustain the fusion reactions. This is where neutral beam injection comes in. This technique is vital for adding the necessary energy to the plasma. High-energy neutral particles are injected into the plasma, colliding with the plasma particles and transferring their energy, much like a cue ball striking other balls on a pool table. This collision process is crucial for maintaining the high temperatures needed for fusion. This process further heats the plasma, pushing it closer to the ignition point of fusion. Achieving this ignition point is the ultimate goal, as it signifies the start of sustained fusion reactions. A balancing act, artificial gravity and plasma stability. Maintaining a stable plasma at such extreme temperatures is one of the biggest challenges in fusion research. This is where the Sun in a Jar Reactor introduces another groundbreaking innovation: artificial gravity. By rotating the plasma at incredibly high speeds within the torus, the reactor creates a centrifugal force that acts like gravity, pulling the plasma outwards. This artificial gravity serves as a counterbalance to the plasma's natural tendency to expand and escape confinement. Imagine a spinning top staying upright due to its rotation. Similarly, the artificial gravity generated within the torus helps to stabilize the plasma, preventing it from collapsing or touching the reactor walls. The conductor. The Sun in a Jar Reactor is a complex symphony of technology requiring constant monitoring and adjustment to maintain the delicate balance needed for fusion. This intricate process involves numerous variables that must be precisely controlled to achieve the desired outcome. This is where McGinty AI's advanced artificial intelligence system takes center stage. The AI is designed to handle the immense complexity and rapid changes inherent in fusion reactions. The AI acts as the conductor of this technological orchestra, constantly analyzing data from thousands of sensors placed throughout the reactor. These sensors provide real-time feedback on the reactor's status. With every passing nanosecond, the AI receives a torrent of information about the plasma's temperature, density, pressure, and stability. This continuous stream of data is essential for maintaining the delicate balance required for sustained fusion. It uses this data to make real-time adjustments to the MWave field, magnetic confinement system, and heating systems, ensuring the plasma remains stable and the fusion reaction continues smoothly. These adjustments are critical to the reactor's performance. The AI's ability to process vast amounts of data and make instantaneous decisions is crucial to the reactor's safe and efficient operation. Without this advanced AI, managing the reactor would be nearly impossible, highlighting the importance of McGinty AI in the future of fusion energy. Fusion's embrace. The Graphene-ZPE shell. Encasing the entire reactor core is a final layer of technological brilliance. A shell made of Graphene-ZPE, a revolutionary material developed by McGinty AI. This material possesses incredible strength and heat resistance, capable of withstanding the intense conditions present during fusion. But its true marvel lies in its ability to capture and convert the energy released by the fusion reaction. The Graphene-ZPE shell acts like a giant energy sponge, absorbing the high-energy neutrons produced during fusion. These neutrons collide with the atoms within the Graphene-ZPE, transferring their energy and generating heat. This heat is then captured and converted into electricity with remarkable efficiency, making the Sun in a Jar Reactor a clean and sustainable energy source. A brighter future: clean energy from a star on Earth. The Sun in a Jar Reactor represents a paradigm shift in energy production. By replicating the process that powers the Sun, we can unlock a virtually limitless source of clean energy, free from the constraints and environmental consequences of fossil fuels. This revolutionary technology has the potential to transform our world, powering our cities, industries, and transportation systems with minimal environmental impact. Imagine a future where concerns about energy scarcity and climate change become a distant memory. The Sun in a Jar Reactor offers a glimpse into this bright future, a future where humanity and nature can thrive in harmony, powered by the very same forces that ignite the stars.